My name is Alex Pavlak. I'm Program Director for the chapter. I want to welcome you all here tonight to listen to Dr. Weener talk to us about his work at NTSB. I want to thank Johns Hopkins Applied Physics Laboratory for offering the facilities to us tonight. I'd like to remind you all that this event will be broadcast live on YouTube, so we will hold questions till the end, and we'll use the microphone so that the people can hear whatever questions you have you would like to pose to Dr. Weener. We won last round with the green tickets. Everybody has a green ticket. I think we're all set there. So without any further ado, why don't we get started? Dr. Weener.
Yeah. Well, thank you, Alex. Thank you for the opportunity to talk about what the NTSB does, and maybe correlate it a bit to system engineering. As was described in the flyer for this meeting, I had a period of about 5 years where I was responsible for, as chief engineer for system engineering at the Boeing Commercial Airplane Company. Really the subtitle was try to figure out what system engineering is and how it applies to commercial airplanes, and then see what you can put in place. So I tend to look at things a little bit from the system engineering side. How many civil engineers do we have here tonight? Just as I expected. And we tend to think of system engineering as something that is applied to complex systems, human interface, and of course its genesis tended to be on the military side. But it also applies to bridges and tunnels. Now the NTSB, let me start off by a word from our sponsor, if you will. Most of you are probably not familiar with the NTSB other than what you see in a newspaper. Some disaster happened, NTSB is sending investigators. We're a small agency, about 400 people. We've got a very highly skilled workforce. We've got a lot of Ph.D.s, M.D.s, and so forth. But as a small agency, we report directly to Congress. That keeps us a bit out of the politics. The agency is run by a collegial board of 5 board members, 4 at the moment. Board members are appointed by the President and confirmed by the Senate. We have fixed terms that rotate every year. Somebody's term runs out. So that helps to insulate us a little bit more from the politics as well in Washington, D.C. But our charter is to investigate accidents, provide improvements for safety. So by safety, we're often thought of as being the aviation safety board, but in fact we cover all modes of transportation as evidenced by the title here. We're going to talk about tunnels and bridges and how engineering can go awry and end up with a disaster. So our stock and trade are safety recommendations. We don't own any recommendations. We don't own any policy. We can't make anybody do anything. So the safety recommendations that we come up with are put in place by arm twisting, seduction, coercion, however we can make a safety improvement. By law, we are to investigate and determine a probable cause of all aviation accidents, and then significant accidents in the other modes: rail, pipeline, highway, marine. So we have specialists and divisions in all of those areas. So that's a little bit about the NTSB. What I'm going to talk about tonight, I'd like to relate a little bit to the generalized, what I call generalized system engineering V, starting with the requirements and ending up with a system. So as we go through the 2 accidents that I'm going to talk about, kind of keep this in mind and see where things fit. So let me start with an accident that happened in 2007. Minneapolis, August 1, 6 o'clock in the evening. Interstate 35 West runs through Minneapolis along with 35 East. It runs through right near the downtown district. The bridge over the Mississippi River at that point is what we're going to talk about. Unfortunately, when I tried the presentation, it looks like some drivers got misplaced, so I can't play a video, but we were fortunate enough to have a video that started just after the bridge started to move and followed it through the river. But let me point out one thing here. As you look at the shape of the bridge, notice the little bit of a dip here. That's where the collapse started. That's the part that is falling initially, and we'll talk about that in a lot more detail. So this camera was a surveillance camera. We don't often have the good fortune of having this kind of information. This is what it looked like. The bridge overall was about 1,900 feet long from the approaches to the north all the way to the south. The center section that fell into the water was 456 feet long. It fell 115 feet into the water. But you can see other parts of the bridge, particularly those parts that were, if you will, on rollers for thermal expansion. Those parts kind of folded up or fell over. So there were 13 people who died, 145 people who were injured. There were 111 vehicles on the bridge at the time of the accident. 17 of those were fished out of the river or were on the part that fell into the water itself. The center section of the bridge, basically the center half, you have a quarter in the north approach, quarter in the south approach. The center half is about 1,000 feet long. That's the section that's the truss bridge. Now, let me talk a little bit about truss bridges. In a pure truss bridge, all of the components are either in tension or in compression, but pure tension, pure compression. In an ideal truss bridge, all of the connections are pin joints so that there's no bending moment transferred from one to another. So everything is purely compression and tension. With a large complex bridge like this, you can't really do that, so you have what you call gusset plates, which you bolt or rivet the diagonals and the verticals and the chords to, and so you get some secondary transfer of motion of moments in that process. There were 13 piers, 14 sections, but as you can see, the biggest section in the middle, the 500-foot long section, is one truss span. The probable cause, as you can see here, and I'll talk in more detail about how we got to that probable cause, is the inadequate load capacity due to design errors in the gussets at the U10 connection, and I'll define that in a moment, by the engineering consulting firm responsible for the bridge design, and the failure was substantial increases in the weight of the bridge resulting from bridge modifications, as well as traffic and concentrated construction loads on the bridge the day of the collapse. Contributing factors: design error wasn't caught by the firm's quality control. The gusset plate calculations were assumed. They weren't made. I don't know how many of you have encountered situations where you assume something is adequate strength or adequate capability, only to find out that that's the one thing that bites you. Contributing to the accident was the practice of giving inadequate attention to gusset plates during inspections and excluding them from load rating analysis. And I'll show you in a moment some pictures of gusset plates that were bowed, which should have been a tip-off that the plates were not within the design loads. So this is a gusset plate. You can see at this node, this is an upper 10 node. The diagonals either transfer loads in tension or compression. So this diagonal is in compression, this diagonal is in tension. Or on this gusset plate, this is getting compressive forces, this is tensile forces. This is just a bigger picture of the gusset. The gusset on this bridge, this is a piece of steel that's about 9 feet in width and about 6 feet in height. This was the initial failure. The U10 means it's the 10th node from the center. U means the upper, and then in a moment you'll see either W or E on them. W means they were on the west side of the bridge, E is on the east side of the bridge. But this is what the initial instability was when the bridge gave way. This is the start of it. You can see the compression here is ripped through the gusset plate. Now the bridge was initially designed in '64, put into service in '67, and 10 years later they decided that they needed to provide some more protection for the rebar in the bridge deck, so they added 2 inches of concrete on top of the roadway that they had. That was about 3 million pounds, which increased the load on the bridge by, as you see, 13%. Kind of creeping requirements. You've never encountered that before, I'm sure. In '88, they had to put some improvements to the medians and the barriers on the outside railings. That added another 6% to the dead load on the bridge. So now you've got about 20% more load on the bridge than what it was initially intended to have. Now, obviously, there was some design margin in there, but by the time the accident happened, the traffic on that bridge was more than double what it was intended to have. In the particular case of the accident day, they were, again, working on the roadway. They were milling 2 inches of concrete off and replacing it with 2 fresh inches of concrete. So they had parked or accumulated on the bridge span about 300,000 pounds of aggregate, stone, sand, cement, and another about 200,000 pounds of water, trucks, personnel, equipment, and so forth. So they had quite a load on that bridge. And by the way, notice where that sand and gravel is, right over node 10. Now, somebody had asked, is this okay to do? And the answer was, oh, sure. So that's the setup. You've got rush hour. You've got 2 lanes closed in both directions. So you've got the rush hour traffic plus all of this aggregate on the bridge. This just happened to be taken that day of the accident. One of the police helicopters or traffic helicopters took the pictures. So this allowed us to verify basically what was on the bridge. The gusset plates were assumed to be strong enough. And that was pretty much standard practice in civil engineering for bridges at the time. Gusset plates were always assumed to be stronger than the members that they were tying to. This is the fracture pattern for the U10 compression diagonal. This is pretty much the way the member broke off. I should say broke off. It translated sideways. You'll see when we take a look at some finite element analysis, the loads were such that the gusset plate really became quite plastic around that joint here and allowed the member to move to the side. Of course, once it moved to the side, and given the fact that this was a single load path structure, one failure is all it takes to take out the whole bridge. So this is the initial compression failure, tension fracture. Now, one of the things that was not done was any sort of analysis of the gusset plate, as I said. We, at the NTSB, decided to do a finite element analysis of it. So along with New York College, Federal Highway, and Dassault Systems, did a finite element modeling of the gusset plate. So this is what the dead load of the original 1967 configuration was. And just for point out, allowable stress and yield stress. Yield stress is where it starts to be shown in red. Allowable means that the structure is certainly going to suffer no damage, no degradation at all at those loads. But yields means that when it flexes, it won't return to the same position, or it will not sustain the load. So already in the 67 bridge design, you can see areas here where the stress in the gusset plate exceeds yield stress. But there's enough area around it that still has allowables, so it holds the compression diagonal in place. But if we look at after the 1977 and 98 modifications, which I said added the dead load of about 20% onto the bridge, you can see how this is turning into basically a plastic flow in this area of stress. So this is exceeding yield stress. Now, if you add the loads at the time of the accident, you see a very large area, and you see it coming down to the sides and going off to the edge. And by the way, there were no edge stiffeners on this. This is just a half-inch steel plate. So nothing keeping it from bowing other than just the integrity of the plate. So this is the area that gave way. If we look at it from the side, basically, this is a diagonal, this is an end-on view. Notice the gusset plate here has started to bend. And of course, once it starts to bow, it's lost its structural integrity. Had it been a 1-inch thick instead of half-inch thick, these would be the loads at the accident time. This is what it should have been. Again, this was an assumption that half-inch gusset plates were thick enough. In some places, they used 1-inch thick gusset plates. This particular one, they didn't happen to do that. Now, as I said, this is the upper 10th node, east side and west side. The west side is where the aggregate was placed, so that had a higher load. And you can see here where the load was, in fact, in the plastic flow. That's the highest stress. So this is what happened. That moved to the side, that caused it to buckle, that then caused the whole bridge to pull away, and the whole thing came down. The fact that there were not more fatalities is really astounding. This is what it looked like. There were 17 automobiles either in the water or on this section of the bridge. And the 13 fatalities occurred in this area. So how did the bridge get designed this way? There were plenty of people who had designed standards. There's the Association of State Highway Officials, American Association of State Highway Officials, and then the American Association of State Highway Transportation Officials changed from AASHTO to AASHTO. You can kind of see why they may have made that change. Between AASHTO and Minnesota Department of Transportation, that's where the bridge design requirements came from. There were some construction information standards from the Federal Highway Administration as well as from MDOT. This was a complex enough structure that they went outside and hired a consulting firm to do the project management. This is a picture of that particular U10 plate. They were required to have an inspection program. The inspection program basically amounted to go out and take pictures. When they came across a bow here, that was explained away. It was explained away by, well, it must have been that way since it was first fit up, and so that's a construction problem. And because it's lasted all these years, it must not be a problem. You know, the interesting thing about rare events is the propensity for people to explain them away. Every remote event can be explained away to somebody's satisfaction. So the University of Minnesota, along with a contractor, took all of these pictures, gave them to a consulting engineer. He looked at him and he said, oh, that must have been a fit-up problem. Again, just explained it away. So if we look at it in terms of missed opportunities, opportunities to have found the problem before the catastrophic failure, the design, construction, and inspection guidance focused on members and structural elements only. So the diagonals, the chords, the verticals were what we're focused on, not on the gusset plates. As I mentioned, the bridge safety inspection engineer noticed but made assumptions about the bowed plate and just didn't document it. And the evaluations by University of Minnesota identified the bow, captured it in photographs, and that was nice to have, but somebody should have looked at the photographs. So it's one thing to have an inspection regimen. It's another thing to actually do something with that inspection data. I know nobody here has ever gathered all kinds of data and then didn't know what to do with it, but and there was a decision to allow staging of the sand, gravel, cement, and the equipment on the bridge deck. It's interesting once you have an accident to then start looking around to say what happened in this accident. Are there similar bridges around? Are there similar situations? And in fact, there were quite a number. The recommendations to take a look at the gusset plates, not only from the strength side, make sure the design was okay, but as the structure rusts, the plates, some of the strength, some of the material rusts away, so you end up with a diminished capability in the gusset plates. 10 states had designs that were found deficient. And that's often the case. So where were the problems on the system engineering V? You know, we started up here with the concept of operations. The requirements for, or the anticipated loads on the bridge were underestimated. The traffic growth was underestimated. There was no requirement for looking at the design capability of the gussets. That's really in the detailed design area. But in operation and maintenance, over the years, the bridge was inspected, but the problems on the bridge were not found. So let me go from a bridge to a tunnel. I think most of you are familiar, have heard the term big dig from one time or another. It's the most expensive infrastructure project in the history of the United States. It's also one of the most, it went on much longer than what was anticipated. It went on about a decade longer than expected. It's the Central Artery and Tunnel Project is the official name of it. It's a project to get traffic through Boston and then traffic to the airport through the Ted Williams Tunnel. And the D Street portal is where the accident occurred, and that's located right here. It's on the way from, and in this particular case it was eastbound traffic. So you can see it connects I-90 to the Ted Williams Tunnel. From the air, this is the eastbound tunnel. 2 lanes of traffic here, 1 lane of traffic eastbound here. The portal was actually a concrete pad, about 5 to 7 feet thick concrete. And it was used as a staging area early in the construction. But the name D Street Portal is because this is D Street, and it goes over top. So 1 or 2 lanes in this direction, 2 lanes in this direction, 1 lane acceleration lane here. If you were inside the tunnel looking toward the flow of traffic coming toward you, this is the single lane, this is an 18-foot wide lane, these are a pair of 12-foot wide lanes. You can see the ceiling structure here, and that's the real subject. Now, this happened in 2006, about a year before the Minneapolis bridge collapse. I remember hearing news accounts of the ceiling collapse in the Big Dig Tunnel. And of course, my concept of ceiling panels were something like ceiling panels that you have here. They must be light. How could anybody get hurt with a ceiling panel like this coming down on your head? But these things are really like pieces of sidewalk. They're 4-inch thick reinforced concrete. Panels are typically 8 foot wide, 12 foot long. Some panels 6 foot by 8 foot. 6 foot by 8 foot weighs about 2,600 pounds. The full panel weighs about 5,300 pounds. So that's more than 2.5 tons. They had to be that massive because this is used as a ventilation duct up here. Some fairly complex requirements for venting air out here and through the vents around the sides here. This is what the collapse looked like. 10 panels came down. Here's one panel still hanging up. This occurred at 11 o'clock at night. There was only one car underneath that. But there is a car under here. A 91 Buick. And the passenger, the husband and wife, headed out to the airport. The passenger didn't make it. And neither did my laser. Had that been rush hour traffic like the Minneapolis bridge collapse at 6 o'clock in the evening, there would have been a lot more fatalities. So what happened? Well, they anchored the ceiling in place with epoxy. But they didn't recognize ahead of time that the characteristic of epoxy was, under certain cases, the polymer can creep. Thanks, Alex. But somebody knew about this. The manufacturer of the polymer knew it. The contractor who was putting the epoxy in was aware of it, but the project consultants and the management didn't. But the epoxy provider didn't really pass that information along. Contributing factors was the unsuitability of the epoxy in previous anchor applications. They tested this out. In the process of trying to decide how to put the ceiling panels in, they looked at what they call undercut. You make a hole and then you cut in that hole, widen it so that you can put an anchor up there. So if you're going to hang a heavy picture, and if you're familiar with the term molly, you drill a hole, you have a wing clip kind of device that you put in, put it through the hole, it expands, and you now have an undercut. Or you can put it in by friction, put in an anchor that expands and holds by friction, or you can epoxy it in, glue it in. So the decision was, because of the cost considerations, to epoxy them in. They did a test and found that the anchors displaced after a short period of time. So again, explaining away test results, they argued that, well, this is two-part epoxy. It's kind of difficult to mix. When you mix it up, you don't get a nice consistent mixed epoxy. So when you put it in a hole, you may have a poor mix. Or you may have voids. You may have gotten air because you're doing this overhead. You're putting it into a hole that is open at the bottom. So again, it's rationalization of unusual events, things that in the safety business we see altogether too often. Once they saw the anchors displaced, it should have been a flag to say we need to watch this much more carefully, but they didn't. They had an inspection program that was required. They designed the inspection program, but they didn't implement it. So this is another drawing of the tunnel ceiling. The ceiling, of course, would go all the way to the side. These are the concrete panels that are hanging in a steel T-beam. After the accident, the accident happened on the eastbound tunnel lanes. The westbound tunnel lanes were examined, and here's what they found. A whole lot of the anchors. In fact, in one stretch of the tunnel, about half of the anchors were already displaced. This is what the anchor looked like. A 5-inch hole, 3/4 inch, about a 5/8 threaded rod. The hole filled with epoxy, some air maybe at the top. Then a seal plug, a polyethylene plug to keep the epoxy from coming out of the hole while it's curing. So this already diminishes part of the anchor capability. The epoxy provider was well aware of a standard set epoxy and a fast set. The fast set epoxy was preferred for the installation because they didn't have to wait nearly as long for the epoxy to cure. But the fast set epoxy, over a period of time, had a factor of 14 to 17 more displacement over time. Again, a polymer like epoxy, when it's under a continual load, can flow. Flows very slowly, but it can flow. The standard set epoxy doesn't flow as rapidly as the fast set, but they use fast set epoxy in the tunnel here. So what were the opportunities? Again, the project consultant limited the choice of anchoring system. Didn't want to go undercut, didn't want to go to friction. You know, undercut's difficult to do. Friction, if the cement cracks a little bit, the friction against the sides diminishes, so the load capability diminishes. So those were a couple of reasons why they decided to go with epoxy instead. Lack of clarity on the types of epoxy available. That's the fast set versus standard epoxy. Fast set might have been much more satisfactory, but probably not entirely. Insufficient approval review by the design consultant, which failed to identify the type of epoxy and note the limitations on its use. The epoxy manufacturer did provide literature about creep. But again, once you discover that what you got isn't performing right, you don't identify what the cause is and instead make up some reasons for why you're seeing what you're seeing and merrily go on your way. So they saw anchors coming down or displacing, but they didn't take action and did not resolve it. So, question assumptions, relying on standards and testing that did not properly assess or account for key characteristics of critical infrastructure components, basically the epoxy. Reliance on false assumptions. And again, when the performance requirements change, the front-end V requirements need to be reassessed. So there were plenty of opportunities here. Requirements should have been much more clear about what the properties of epoxy were or what the requirements were for anchoring over a long period of time. There were mistakes in the detailed design because somebody knew that epoxy wasn't the right thing, particularly the fast set, but they used it anyhow. They did a test, but they rationalized the test results away. So again, the system engineering process is really appropriate for civil engineering problems as well. So with that, I'll be happy to take a few questions.
Use the mics. Raise your hand if you have a question.
Can you hear me? Yeah, okay. So in the first example, on the compression diagonal, it almost looked from the photographs that the box section, which was the diagonal piece, it was a box section, I think.
That was a box beam.
Yeah, it almost looked like this, like the top and the bottom sides of that box section sheared as it penetrated the top horizontal.
Yeah, it displaced laterally.
Mm-hmm.
You can just see the bend preceding it. So once it displaced laterally, then it was able to go up through. And once that section of the bridge started to move, the bridge decking is just sitting on top. It's not anchored to it. This is not, nobody bothered to bolt it down because with all that weight, why would you? But then once that shifted, that then took out the other side as well. And at that point, the whole thing started to move and come. It really came down almost, I'm sorry I couldn't show you the video. It came down pretty much as a whole section.
Thank you.
Any other questions? Here.
Looking at the V and then all the slides, the commonality to me seems to be the lack of vision, lack of follow-through, imagination, and looks like there was several opportunities for several people to chime in and make a correction. So, I mean, where is that going to lead us in the future when they try and pinch pennies on things like a space elevator? And if that comes crashing down, wrapping around the Earth 7 times, there might be a whole generation losing space access. I mean, what do you do?
Well, hopefully, by going through this investigation, identifying the way the requirements were mishandled, the way the test results were rationalized. At least quite a number of other bridges got looked at very carefully, and some bridges, in fact, were immediately taken out of service. There are a bunch of bridges. We send these recommendations out, with the recommendations to go inspect the bridges. Those recommendations went out to the 50 states and 4 districts, 4 regionals, to go look at their bridges. So that's our best stock in trade is, here's what you need to do to take a look at, do you have the same problem?
Another question here?
Somewhere back in the 90s, some of the IEEE student magazines, I remember seeing something about monitoring loads on bridges, with a lot of instrumentation, and getting that data, looked at or transmitted. Do they have a program for monitoring bridges in that respect? For data gathering?
I can't tell you in detail because I'm not intimately familiar with it, but I am familiar that some of the newer bridges are instrumented with strain gauges in a number of places, in the critical places, so they can in fact monitor how the bridge is doing. You have to realize this bridge the requirements were laid out in '64, and '67 was when it went into service. So the capabilities for monitoring were much different at that time than they are now.
Question. You mentioned the gusset plate, 6 feet by 9 feet, but only a ½ inch thick. Some were 1 inch thick. I guess the question, was that a conscious decision, or did somebody say, we've got a budget and we need to go with a ½ inch here, and what was it? Was the budget or budgetary pressures involved in undersizing that particular plate in general? And the other question is, are there standards now for once you know what the stress loads are going to be on a particular bridge, building in the a 50% overcapacity or over strength on these items?
Well, you got a two-part question there. I'm not sure we were ever able to go back through the history to figure out who made the decision to use a half-inch gusset plate. But once you have this kind of accident, this kind of situation, the tendency is to make sure, if in fact we do anything, we probably overcorrect the next time around. But 1-inch gusset plate would have, as you saw, would have had a completely acceptable load. The half-inch gusset plate didn't. But the half-inch gusset plate was sized originally for a bridge that was 20% less weight and didn't have the construction loads on it at the time. So it's a combination of things. As usual, when we have a catastrophe, it's usually not one cause. It's a number of things that have accumulated to finally end up with an event.
In one of the last slides discussing the bridge collapse, there was a note to the effect that there are at least 10 bridges that states had identified as being inadequately designed, and the note was that most of those bridges are being constructed in the last 10 years or so. I'm just wondering how that's possible given the design and analysis tools that have been available for at least the last 20 years or so.
Well, having a tool available and using a tool are two different things. One of the things that we try to highlight in this report is the need for some careful analysis, particularly analysis of loads on a truss bridge, loads like gusset loads. But there's also kind of at least some encouragement to use a different kind of bridge, because truss bridges tend to be single load path structures. And you know, I come from the aeronautical field where we don't like single load paths anything. You make sure that you've got redundant load paths. You can build a bridge with redundant load paths, but it's probably more expensive. Truss bridges are quite economical.
Two-part question. First question is, over the last 20 years, how many failures of these kinds of bridges have there been? That's the first question. And the second question is, when you look at however many of those failures that occurred, how many of them were due to gusset plate failures?
Well, I don't have enough history in civil engineering to tell you that.
And then there's actually a third part, which would be, if you knew what the past was, then couldn't you have used that to make predictions about the future as to what the nature of the inspections are that you would want to perform?
Well, there were inspection regimens for the bridges. But as you saw, some of the inspection regimen just documented some of the conditions and didn't do anything with it. The recommendations that came out following the investigation focused not only on the design of gusset plates, but on the continued operational maintenance of the gusset plates, particularly with regard to corrosion, because there's only one direction that steel goes, and that's it gets weaker as it corrodes.
I'm sorry. What sort of a safety factor do these bridges get designed to? What you talked about, the loads being 20% higher than design, but that doesn't sound like a big number to me. I would think it would be 300% safety factor. What sort of safety factor is practical?
I can't tell you what it is in general. For some of the members in here, though, that were part of the report, the factor was 3. So you have your max operational load and then the safety factor of 3 above that. Had the gusset plate been 1-inch steel, it would have been just fine, because the loads, even on the day of the accident, were all on the allowable side. So, you know, you've got some margin on over the allowable, but you don't really want to use it. One more.
The forensics about the bulging of the gusset and the failure of the inspectors to recognize that as a hazard, has that led to any extra training or a recognition that maybe the people who are doing these inspections don't have the necessary information to make good decisions?
Yeah, one of the things to come out of it is a bridge inspector training course that is now in use. How extensive it is, I don't really know, but it certainly was one of the results of the investigation. Well, thank you very much.